So, by the way, how many of you did the assignment? You know, I extended the time to like, I had like a week extra. So at the end of the day, when I checked the sheets, the assignment sheet, I saw just 14. Hello. I saw just 14 submissions. And I'm like, I don't understand how we have 14 submissions and at the end of the day, we have over 50 people showing up every week. Sorry, is it 100 and something? Okay, today on the low side, you just have over 50 people. It's just 14. Like, is it that we have ghost students? So like, left for me today, I just don't feel like even doing much. I just felt like let's just go through what we have done so far. If we have just 14, it's not impressive. Let's be honest. Like you're wasting our time. But I know some people are actually doing the assignment. Like some of them are actually on Slack. They boss, either they boss each or they boss some other people, and I think that's good. I'm not saying you should boss people on Slack. I'm just saying you should do the assignment. Like I just feel that if you have any challenge, you should try to drop it on Slack. Someone will definitely attend to you than just coming to the class and not doing the assignment. You get to do something else and it's going to be difficult. It's going to be as difficult as, if not more complicated than the last one. And the point of doing the assignment so you can experience these difficulties, then you can see your knowledge, feel your knowledge gap where you are having some deficiency. You can feel that as fast as possible rather than just come and still do the same thing and move on. So personally today, I don't know whether we should do logistic regression, but probably I will just do some introduction, then next week we'll just continue. So what is the major reason why you're not doing the assignment? I want to know your pain. Like, I understand. It's difficult, but let me feel your pain. Just tell me, like, I want to know. You don't know what's going on. Did you attend the first class? You're attending the second one? You're in the third one now. Okay, this is the fourth one. Wow. So what is the problem? Tell me, what's the problem? Is it difficult? Or is it because you have to recite it? I don't know. Like what? Actually, I'm not supposed to be in the data science class. You are okay, already did that. Okay, good, okay, fine, that's good. So, any other person? Yeah.
And then we went into the next one, like use SQL. I'm like, okay, so what am I supposed to do differently from the initial one? And then when I was thinking, I'm like, nobody does all these things. I'm like, what's up? Why are we doing this way?
Can you break your question down? The first question is what? Just say it how you do. Just say it like that. Just say it.
And the first class, like the univariate regression.
Yeah.
After the data ranking, the remaining part. But then, last week he explained it better. But then there were still some doubts.
What doubts?
Am I doing the right thing?
What makes you think you are doing the wrong thing? You have to be specific with your doubts. So, any other one? You don't understand the SQL. Initially, you won't understand the SQL. That's how SQL is. But the whole point of using the SQL is that you won't build your model from scratch every now and then. Like you're not going to use like NumPy to build your model. Okay. Who has been doing that?
No, there's not with SQL.
It's okay with SQL.
Like you didn't get it, so why are we using it?
Okay, you know what? I'm not going to, this is what I'm going to do. I'm going to explain the procedure, how you are going to do it.
Okay.
Then, next week, if the assignment is not up to 20, I have the treasure. In fact, I've actually selected like 3 or 4 people that will come and explain their assignment. I wanted it to be like that, but I don't know. I just feel that maybe I should do it myself, or should I just get them to explain their assignment? So they will be, I believe they will be in a better position to explain their assignment, right? So I should just call like 4 people that will do that. Yeah. I think I should do that. Then what I will do, I will explain the procedure of how you are going to use the sklearn. Then from there, next week, if it's not up to 20, if it's not up to 20, okay, you guys should submit. Let it get up to 20. If it's up to 20, I'll do the assignment. I'm not saying you should just add 6 because it's 14. So, okay. Any other question? Yeah. I can't hear you, please. Can you speak up? It's up. What part of the issue are you having? What kind of error are you having? You have to be specific with your error. I can't help you if you are not specific. Like, later, we'll discuss about that later. So, anyone? Please, can you speak up, please? Yeah? Sure, okay. It's actually on the kit. Okay. You know what? I'll do that next week. So I'll do that. I can't hear you. Yeah, this is how you submit. You clone the repo on GitHub. Then when you clone the repo on GitHub, before you clone the repo, fork the repo on GitHub. Then you clone it. You have it on your local device. Then from there, since you have already forked the repo, so you can as well as push to your own. You can push to your repo online. So what you send us your GitHub username or the URL of the assignment. You just send it to us so you can locate where your assignment is. So any other question? Yeah. Okay. Yeah, that's why it's part of the assignment. But you are right. There's a part, I think week 6 or week 7, either one, week 7 or week 8, we'll discuss that. In the future, we'll discuss that. But you are right. But that's how you do that. You know, let me just explain the procedure so you go back and do your assignment. I've not used psychic learning in a while, but we'll be fine. We'll figure it out. So I'm not going to explain how you are going to do it. So, let's say you have your data, X, Y, I, 1, so, okay, let's say this is 0, so, 100. So, this is what you are going to do. Let's stick with univariate linear regression. This is what you are going to do. You will load your data. The normal procedure, you load your data. Probably you use pandas to load your data, or you use NumPy, anyone. But let's think you use pandas to load your data. So after loading your data, the next step you are going to do is probably import your Then when you import your scikit-learn is just like it's a tool for building model. either linear regression model or logistic regression model, neural network, any kind of model, decision tree, you find everything in scikit-learn. So what you're going to do is, you look for how to import linear regression. Linear regression, I think that's what they call it in scikit-learn. So after doing that, you have like your model. Let's call it, our model is this is our model. The first thing is you get your model. This model. Then the second thing is based on what you said now. I think it's very important, but we have not actually discussed that. You're supposed to like split your data into 2 parts. Naturally, it's 3 parts to split your data, but for this case, let's just split it into 2 parts. You're going to have your train and your test. And let's say the ratio is 70-30. So you should split that. That means you have, okay, this 70-30. So in scikit-learn, there's something called, what do they call that thing again? What do you split? Train test. Yeah? Train test. Yeah. Train. Split. So this will handle 70. This will split your data set into 2, right? But there's something that I've noticed that will reoccurring. The mistake people do most times is that they split both. No, this is the mistake I've noticed so far. They pass the y and no. Let me talk about normalization. Before we get there, let me talk about normalization. So after splitting your data set into 30, 70. So this particular one here, this is what you are going to use to train, this is what you are going to use to test. So you send this guy to the model, right? You send this guy to the model, use it to train. Then from there, you can do your prediction. So this is what before I go there, your pre-processing step, one of the steps is feature scaling, right? So what I've noticed is that when people do feature scaling, they do feature scaling for both X and Y. Can someone tell me the reason why you should not do feature scaling for Y? That's your output. If you should scale your app, what will happen?
It will affect the initial.
What? There are 2 things. Either you scale, if you scale your output, you have to also multiply it back. Let's say, let me just give you an instance. Let's say you do feature normalization. You want it to be between 0 and 1, right? Fine. Your output is, let's say it used to be 1 to 10. But now it's what? 0 and 1. That is between 0 and 1, right? You understand what I'm saying? After scaling, it's between 0 and 1. And let's say you want to predict. What you predicted is 0.9. So what's the equivalent of 0.9? 0.9. 0.9 is what? Is 9, right? 0.9 is 9. So if you are going to do feature scaling, what does it mean? At the end of the day, you are going to multiply by this, by 10, by the upper bound. But you can as well as not do feature scaling. You leave your Y value. So you do your feature scaling on the X values. Make sense? Yeah. So this is something that I kind of noticed. Like I want you, like some people were asking, okay, why is it that when I made my prediction, I was getting something else. I was getting a small value. I was getting negative. So this is like one of the major reasons you are getting negative. Yeah.
When I was doing computer, I saw you mentioned that normally we try to do linear regression that the model takes
the model already takes care of feature scaling. So why do you do feature scaling?
Like to balance of the ratio of the value, for example, like maybe you have a feature like million.
Magnitude of this, yeah, this year.
So I think that's give you the like
This is the cyclic length handles feature scaling.
the class, like the linear regression class, cyclic
I don't think so. Because in scikit learning, there are feature scaling methods. We have like functions, sorry. We have like standard, you have standard, you have mini max, you have standard, you have like normalizer, you have like 3 or 4. So it's trying to tell me that there's something that's already available, and because you're using linear regressor, you don't necessarily have to do feature scaling. It doesn't really make any sense to me. You understand my point is that you already have them there. Why can't you just use them? So you do feature scaling. That is part of your preprocessing. So what you do is that you scale these values, right? These are the values you should scale. But if you want to scale both of them, you are allowed, you can scale both of them. But what you should always remember is that at the end of the day, you multiply by this magnitude, your upper bound. It's more or less you're going to do interpolation. You understand? Multiply by the upper bound. So after doing your feature scaling, after doing this, you push it to your model, you train with your linear regressor, then you make your prediction. So now, if you want to test to see how good your model is, you use you're supposed to have your validation step, but we are going to talk about that later. So use this to test to see whether your model is whether it makes any sense or not, whether you're going to retrain or do something else. So do you guys understand this step? So the first step is to call your model. You look for linear regressor in scikit-learn. But before you do that, you have to split your data into 2 parts. You have your train and your test using train test split. After doing that, you train what? You train your X values. You train your input values, your independent values. You train them, then you're going to use both your independent and dependent values, but you do feature scaling on your independent values. I'm sorry, you do feature scaling on your independent values. If you're going to do for your dependent values, you have to consider the magnitudes, you have to consider the range. So after doing that, then you test. So these are like the procedure. It's not really that difficult. So what your worries are is how to use this guy. The second one is how to use this guy. And the third one is probably how to predict with scikit-learn. I believe that's what your worries. And I think in scikit-learn it's just a model.fit, something like that. It's not really that complicated. So, any question? The procedure. Okay. Let me state the procedure. Let's start from the data. What are you going to do to the data? The first thing. Let's do feature scaling. Right? So the first thing is normalization. Let's say feature scaling. After scaling the features, then what are you going to do? You split it into 2. So then what's the third procedure? What's the third procedure? You train with what? Then what's the last procedure? After training, this is basic. This is just basic, but there's a lot you can do between. This is just like for this problem, but in real life, there's a lot you can do before you get to like. This is just basic. What you have to do for this assignment. So you do this with your you look for that. You look probably standard meaning, normalize it, whatever one, and you have to give me a reason why you're using that feature scale. What type of feature scale you're using? This one, you use your train split. This one, model.fit. This one, model.predict. So fit, predict, train test split, maybe standard meaning. You have standard, you have normalizer, you have standard, you have meaning something. Yeah. So, standard meaning, I believe standard meaning. Simple steps, not really that complicated. So after this, I expect like 30 or 40. Train with, sorry, train with, that's it. So let me just model.predict. That's all. Any question? What do you say? Why should you scale Y? Why? You can scale it, you cannot, I don't know, like, it's up to you. But I would advise you not to do that, because if you should scale Y, you're going to, you have to take it to the original original value. You have to take it to the original value. But yeah, exactly. It's just that the mistake people do sometimes is that when they pass their data, they don't pass it just they're supposed to pass just X, but they pass both X and Y. So our advice is just to pass just your input. Yeah. You don't scale it. If you don't rescale it, the values, your predictions won't make any sense. You start having negative prediction, and except that's why I would advise you to leave it alone. Just stick with your input, leave your output alone. So someone can be adventurous, can give both of them a try. So, all right, I think let's just do. I won't really talk much. Yeah, another thing I want to say is the resolution. Yeah, the resolution, because you know when you are trying to like get the original value by multiplying it with something, I believe it must have lost some resolution. Like yeah, so why can't you just leave it like that? Yeah, resolution. That's nothing is resolution. That is what you wanted me to say. Thank you. So I think that's all for today. So let's just talk about logistic regression. So in this logistic regression, what's the time? This class is supposed to end by 4, right? No, it's 4. I like what you guys did last week. So once it's 4, we're good to go. Yeah. So this class is going to end by 4. But I'm going to give you like an overview of what logistic regression is all about. Probably next week we'll go through it in depth. Yeah, I don't want to like bore you with some stuff. So we'll just talk about we'll have like an overview of what logistic regression is. Then next week we'll go into it. We'll go in depth. So this week, since you've already done like a lot of maths already, so sorry, you've already done a lot of maths. So I don't want to I don't want you guys to write too much. You're already written so much today. So I might skip some slides, but next week you're going to go back. Or if you guys still want to do some maths, be my guest. So I will skip some slides just to make sure that I want everyone to be comfortable in this class. So I will skip some slides that I think that might be technical. All right. Well, what kind of question do you have? I asked, is there any question? I can wait. After the class, you can ask your question. Well, let me see. Okay. I think I'll talk about that today. So, this is what I'll talk about that later today. So, let's just talk about this. So, what can we observe from this view? What can we observe? We have two what? We have two items, right? Two fruits. We have orange and what? Apple. So, this is not like what you have been doing so far, which is what? You are predicting continuous value, right? You're talking about predicting district values. So either it's in this class or it's in another class. So when it comes to logistic regression, dealing with district targets, both input and output, you're just dealing with both. You're dealing with district target. So here you're trying to giving previous history or giving previous pictures of oranges or apples. Can you predict whether this whether a picture is orange or apple? Like given the history, given what you have trained your model with, can you predict whether this picture, whether this fruit is either orange or apple? That's for this case. So before that, let us do some kind of revision. So in machine learning, we have supervised and unsupervised, right? And for the supervised case, first of all, let's just do like a brief review. So what is supervised learning? When you have what? Can someone just stop? When you have what? You have the labeled data. Why for the unsupervised? You don't have yet. So for the machine learning, for the supervised learning, you have labeled data. Right? Why for the unsupervised learning, you don't have labeled data? What you are trying to do, you're trying to get the structure behind the data. You're trying to predict patterns behind the data. And most times you're talking about clustering and some other stuff. So but this is what I'm talking about. Today we're talking about supervised learning, another type of supervised learning, which is what? Which is logistic regression, which is classification problem. So in logistic regression or classification, you're trying to identify a unique class, a district value, a boolean or categories. So you're trying to, for what you're trying to do, you're trying to fit a model that will fit these data points. But again, you're not trying to fit a model. You're not trying to use a model that will fit data points. You're trying to use a model that will separate these two data points. You can see this diagram, right? So you're looking for a model that will demarcate this class from the other class. You understand? So this is what logistic regression is all about. So, instances. For classification problem, since we are dealing with district values, let me just give you an instance. Like in Google Mail, your Gmail, you see you have like 4 or 5 tabs. You see social, you see promotion, primary, updates. I think God, so that one. Spam, trash, right? You have different classes. So that's a classification problem. So how do Google know that this message is important to you? How do they know? Probably from the introduction of the message. Probably win $1 million today. I'm just giving you an understand. From history of messages that start with this header, win $1 million today, you know that this message is actually a spam, right? Or hello, you have been selected for so job interview. Kindly stop at like the same location, that location that people have always been complaining about, that when you go there something bad will happen to you. So from history, this is a spam. If you should get something like that, it will automatically, you won't even see it. You won't even show up in your primary. It will just go to your it should just go to your spam. So why for social? You might have like your LinkedIn, add connection. So and so person added you. From the header, this is supposed to be what? Social. So you understand the idea. That's just how we use let's say logistic. You know, they might be using something else. They might be using support vector machine, but it's still a classification problem. So that is for the PO. And for the transaction, I think most of these banks, they use this under fraud detection in order to know whether this transaction is fraudulent or not. Probably giving the person's IP address, giving the time of the day, giving what region the person is. This transaction might likely be fraudulent. I'm not in New York, but my card is being used in New York, and I've not traveled. Something must have gone wrong. So something like that. I'm just giving an instance. So this transaction might be fraudulent. So it's about fraudulent transaction or non-fraudulent transaction. Why for this? The last case, which is like this is for the medical for healthcare. You might want to classify a cell into. Excuse me. So for the last one, the tumor. Let's say you want to classify if a cell is cancerous or non-cancerous. That's malignant or benign. So if it's malignant, that means it's dangerous. If it's benign, that means it's not dangerous at that moment. So in that situation, you can see this problem is basically a classification problem. Is that yes or no? Or another way you can also see it is like, what are the chances that this thing is, how sure that this thing is cancerous? Am I 90% sure this is cancerous? Am I 30% sure this is cancerous? If it's high, if the probability is high, that means it is malignant, it is dangerous, it's cancerous. But if it's low, it's not cancerous, it's just benign. So these are how you should think about problems. And I can tell you, like, the most important thing in machine learning is not really about using the model. Using the model is actually the easiest part. It's formulation of the problem, like knowing how to formulate the problem. To know that this is the algorithm I'm going to use, this is the approach I'm going to use. That is more important than using this algorithm, because, to be honest with you, with scikit-learn, it's just linear regressor or linear classifier. You just call something and it will do the job. But that moment you don't know that this is a classification problem or a regression problem, I think you have a bigger problem. So let's be honest, like, it's a bigger problem. So it's better you understand. I will advise anyone to understand how to do problem formulation than sticking to the like understanding the tools. Like, when you understand the problem formulation, the tools is even basic for you. You know that this is what I'm going to do. But when you don't understand problem formulation, you struggle with the tools. You won't even know how to use the tools because you don't know how to support what you use. So that's the point. So we'll skip some slides. Next week we'll go into it. I don't want to bore you guys with some stuff. So next slide. So why you should not use linear regression on classification problem. That's what I want to discuss now. So let's say we are trying to. You have your data set. You have a data set, and since you are dealing with classification problem, our output. Let's say we are trying to do cancer detection, right? Cancer cell detection, whether the cell is cancerous or not cancerous, that means malignant or benign. In that situation, how many classes do we have? 2. So our Y is either, let's stick with 0 or 1. Let 0 be what? Let 0 be. Let 0 be. Let 0 be benign. Let 1 be malignant. So 0 means negative. We don't have cancer. 1 means there is presence of cancer in that cell. But that the cell is cancerous. And let's just see this is our input. Let's just say our input is 9.5, 0.4, 0.7. And 1, 2, 3. In this case, let's say 0.9 means that is positive. This one means it's negative. This means it's positive. You understand the problem formulation? So given the picture is 0.9, the value is 0.9. It means that it's positive, right? For this one is 0.4, it means that it's negative. While for this one is positive. Now, how many classes do we have? We have 2 classes, right? So let's say, since we have 2 classes, we have 0 and we have 1, right? And let's say these guys are somewhere here, and the other guys are somewhere here, right? It has to be in between 2. It has to be this guy or that guy. It can't be in between. It's not like what you have been doing so far that can be everywhere. So it has to be in between these 2 classes. And now, let's do what we know how to do best. We apply what? A linear regression. Apply a linear regression on this problem. We are going to do that. How are we going to do it? You can see that we put a line here, right? And this line can demarcate, can separate both data sets, right? This is a class, this is another class, right? So this is like a good separator, right? But now, let's say we have, okay, let's continue. And let's say at this particular point, our y, this value is about 0.5. So anything above 0.5 is positive. Anything below 0.5 is what? Negative. It's just an assumption. It works well. Makes sense, right? But now, let's say we have another value. This value is what? Let's say this value is 20.0, right? Right? It's 20.0, and this is what? This is going to be, let's say this is going to be 1. This 20.0 is somewhere, this is 0 to 1, right? This is 0 to 1. So 20 should be somewhere far, right? Let's just say 20 is here. Now we want to apply your linear regressor. How are you going to do that? To accommodate for this guy. Are you going to do it like this? How are you going to do it? Let's erase this guy. You should do it like this. Must he do what? The last X. This is a straight line. I'm even bending it, to be honest. Like, this is a straight line. This is just a straight line.
And yes, if you study the last one, it might be more straight.
Is this what you're talking about?
Oh,
is it possible? If you should touch this, so what will happen to this guy here? There's still something here. Let's assume, let me redraw this time. I want you to understand. Let me just redraw it so you understand. It's a straight line. Let's have it here. Right? Let's add more values. It's a straight line. And we want to, the first one was like this, but we have a bigger value, which is somewhere here. We can't just apply, let's stick with our straight line. Let's draw it like, this is the best we can do, let's be honest. This is the best we can do. Any other thing you're going to try is going to look like a curve. This is the best thing we can do. We want a line, we don't want a curve. Let's be honest with ourselves, right? So if you should do that, you discover that you have something here, right? And let's say, usually we say 0.5 will separate it. But now, 0.5, you cannot separate it anymore, can it? Can it? Why? We don't have like a clear boundary. Do you have a clear boundary? That boundary is no longer obvious to us. That means we cannot use a line to separate this problem. We can't use a line to solve this problem. We can't use linear regression to solve this problem. You have to reformulate the problem to something else. You have to probably, that is why you need logistic regression. That's why you're doing logistic regression. So we can reformulate this problem in such a way that we can separate these two classes. Does it make any sense? So this is what changed the game. Having something like this. Change our theta. We can't use 0.5 anymore because we can't have like a clear separation. And when we tried something else, it didn't really make any sense because we still have some misclassified values here. So in this particular case, our linear classifier, not linear, our logistic, our regressor kind of sees this guy as positive, right? Usually we say that here in this part you are 0, here in this part you are positive. But here you can see that these values here are also classified with this guy. It's a misclassification, this is misclassification. So you can't use what? You can't use a line to solve this problem. You have to reformulate the problem. That's why you're doing logistic regression. So you understand why you cannot apply linear regression on classification problem. Do you understand? Yes. Or should I ask a question? I don't even know what to ask. I know you have a question.
No, this is not about this topic. It's about local minimum.
We are not doing local minimum. This is, I'm sorry, we are not doing that. So I think that's what I'm trying to describe. Okay, the next slide. So that's it. So if you have another, this is just like, I don't want to say it's an outlier, but it has a big value. It's where it is, you can't use the same classifier. You can't use linear regression for this. You can't just use a straight line for this. And if you should, we can go to the next slide. It has. Can go back. So, one step again. So this is what I'm just trying to say. Applying linear regression to classification problem is a bad idea. That is what you should take out of this class. Like, if this is like the most important thing you get from this class, this should be like, this is the most important thing you should get out of this class. But I want to keep it on, like, I want to give you guys an overview that you don't have to apply, don't apply linear regression on the classification problem. So you have to reformulate the problem. So next slide. Okay. So what we want is, we want something that okay, let me so you guys know what this is, right? Our hypothesis, right? You know what it is, right? So what this basically means is that you want your hypothesis to be in between the range of 0 and 1, right? And your hypothesis is what you are going to decide. It's your guess, it's your idea, it's what you are going to come up with. If it's like a threshold. If it's above this threshold, this is positive. If it's below this threshold, this is negative. For the last instance, for the first instance, it was 0.5. It worked well. But when you got another value, a bigger value, it didn't work well. You could not use 0.5. So that I put that this your hypothesis is what you are going to decide yourself. Like, okay, it's not by definition it's going to be 0.5. You get? It's not by definition it's going to be 0.5. If it's based on my data, if it's this above this particular value, this is what my threshold should be. If it's below this value, this is what my threshold should be. You get the idea? So next. So next. Now, so how can we reformulate the problem? How can we reformulate the problem? So we want to get something like this. We want our values to be between 0 and 1. And to arrive there, there's a particular function called sigmoid function or logistic function. So basically, it is g of x over 1 over 1 plus So this is what it is. But before we get there, the question is going to be, what is it? You guys are familiar with this guy, right? Yes or no? Yes. Is this class boring? Let's be honest, you are familiar with this. You have been doing this all this while. Come on, this is like x0, x1, x plus. This is like what we have been doing all this while. Yeah? This is just like a vectorized form of it. This is what you guys have been doing so far. This is from your linear regression, right? Fine. Now, these values, you know what I'm bringing this back. This is how you load your input, your x1 and x2. Your x0 is your bias, right? This is how you're going to load your input. Your parameter, your model parameter is still your θ1 and your θ0, θ1 and θn. These are your model parameters, right? This is how you load your data with linear regression. You understand? Stick with me. This is how you load your data with linear regression. But now, you want your values to be between 0 and 1. How are you going to do that? You push these values. You apply your logistic function on these values. When you apply a logistic function on these values, it will have like a boundary between 0 and 1 to limit the boundary. It's not just going to be, if you have an outlier, it's still going to bring that outlier. It's going to make the outlier kind of bounded. It's not going to exceed that value. You understand? That situation whereby we have 20, this will bring it down to something close. It's going to be between 0 and 1. Do you understand what I'm saying? So this is the idea. This is what you are familiar with from linear regression. Fine. But now, this, you pass it here. You apply a logistic function to it. When you apply a logistic function to it, you arrive at this. Your value, your output value is going to be between 0 and 1. Does it make any sense? That is magic. Does it make any sense? I'm serious. Does it make any sense? So what's the point of this? What's the point of this? What is this? Let me ask questions. What is this? I now say linear regression. What is this? I know it's from linear regression, but what is this? This is your H, right? But now, your H is not just like a normal H you have your linear regression. So what happened to our H? It has been what? Transformed to something else, right? It has been bounded. That's how you should see it. Before in linear regression, what you do is you predict values, right? Continuous values, you predict continuous values. But now you are also predicting continuous value, but the difference is just that the continuous value you are predicting is bounded. And it is bounded by applying the sigmoid function or logistic function. Does it make any sense? Okay, fine, let me just continue. So you guys will figure it out. Oh? So, let's go back. One at a time. So, if you should apply your logistic function to this value, you should apply it. This is your hypothesis. Now, after applying your logistic function to your value, to your model parameter and your theta and x, this is what you are going to get. This is your hypothesis. We reformulated our hypothesis. This is what we are going to get now. So the question is going to be, how are we going to do that classification? So this is how it works. This is what logistic function looks like graphically. This is what logistic function looks like. It means that, okay, between anything less than 0, anything less than 0 is 0.5. Theta is going to be 0.5. This value, your H is going to be 0.5. Anything here is 0.5. Anything above that is 1. So we are bounded by this is our decision point. This is what separates two classes together. So anything that is of negative to 0 is 0.5. And below that value is one class. Above that value is another class. Does it make any sense? So this is your sigmoid function. I don't want to go into much detail. Next we will do that. So I just want you guys to like understand how this stuff works. Next. So this is just like an instance. Let's say our theta, after applying our logistic function, this is what we got. We got 0.7. So what that means is that it tells that patient has 70% chances of tumor being malignant. Remember what we said? It is remember when we said malignant is what is 1 and benign is what 0. So now I have 0.7 and our threshold. Our threshold is what 0.5, right? So 70 is like 0.7, right? Yeah, from here is 0.7. It means that what? It's close to 1. it means that that patient has 70% chances of having malignant cancer. We'll do this next week. I want me to let's do it next week. How many minutes are left? Next slide. So yes. So now our threshold is what? 0.5, right? Anything above 0.5 is what? Positive. Less than 0.5, negative. So this is it here. Positive, negative. You can see it's not equal or less, it is less. This guy is accommodated for anything equal to 0.5. You understand what I just said now? So, next slide. Next slide, next slide. So let's take this one. So, given these values, we want to have your decision, we want to have like your linear classifier that will separate these two classes together. This is what I'm talking about. You have your let me change this here. So this is G of right. How many values do we have? We have two values, right? 1, 2, 3. We have 3. Let's change this guy to 2, 2. Right? Makes sense. So from here we have what? Theta 0 plus theta what? It's the same thing. But it's still the same thing. But now we have values for our theta. The values of our theta is what? Minus what? 1. This is the value of our theta. This is what? This is a vector, right? This is a vector. So now, minus 3, right? Minus 3, x naught plus theta 1, right? Plus theta, not theta, x1, x2. X1 is what? 1. So this is so now we have what? X1 plus x2. Let's take this guy to the other side. Right? But let's not take it to the other side. Let's just leave it where it is. So now, this value is what we are familiar with. This is what we just did here. But now what we want to do is that we want to apply sigmoid function to this value, right? Come on. This is equivalent to, let me take this guy out. This is equivalent to your Z. This is equivalent to Z, which is where? Which is this point here. This is what we did, right? This is equivalent to Z. And Z is what? Theta transpose X. Now, after doing this, we want to do what? We want to apply logistic functions to it, right? We want to shrink this value. We want it to be between 0 and 1, right? So when you apply this, let's assume. Okay.
Sorry.
I don't want to do the math.
X1 minus 3.
Which one? This one?
X1 minus 3 plus Oh, minus 3 plus X1.
Does it make any sense? Fine. It's fine like this. So what we are going to do is that we are going to apply our logistic function to this to shrink the value between 0 and 1. This is what it is. This is just low level. Next slide. So, if we want to make the point visible, if you want to say that at this particular point, this value is going to be, our value is going to be positive. At this particular point, our value is going to be negative. That line, if you want to know what this line is, like, we want to know our decision boundary. That's what I'm talking about. We want to know our decision boundary without going through, taking it to the sigma, to the logistic function. This is how we are going to do it. We are going to say x1 plus x2. Let's take this guy to the other side. It's 3, right? It's 3.
Yeah.
So the question is going to be, can you go back to the last slide? Can you go to the first system? Remember this part? Come back to this one. This one I'm talking about. Remember this part? Anything less than 0.5 is what? Is 0. I'm supposed to introduce the inequality sign, but I didn't introduce that. I just don't want to make them complicated. But let's introduce the inequality sign. Where are we going to do that? This is where I'm going to do it. So what this thing is just saying is that if I add x1 and x2, if the value is less than 3, it is what? It's 0. If it's above 3, it's 1. So this 3 is like what? Your decision boundary, your decision point. This is what you're going to use to separate two classes. So given, if this value, let's say we have 4 minus 5. Add both of them, what do you have? That's minus 1. And if this is going to be minus 1, right? Let's assume our theta 1 and theta 0. Let's assume all these values are 1. If you should add both of them, what are you going to have? Minus 1, right? Yeah. Is minus 1 less than 3? Yes. It is less than 3. So what's it? It's in one class. It's in 0. It's in the positive. It's in the negative class. If it's above that, let's say we have 10 and 20. That's 30. If you should add both of them, what are you going to get? 30. It's above 3, right? It is what? Positive class. So this is just a way of looking at it without applying the logistic function yet. This is just how to look at it from graphically, from the, if you're going to plot it, this is how you're going to look at it graphically. So basically, can you go back? Can you go forward? So this is, no, so this is what I'm saying. So this is the decision boundary. If I have a value, if my x1 is 2, and my x2 is 1. Okay, x1 is 1 and x2 is 2. 2 plus 3 is what? 3. And we said any is less than, we are not saying equals to, is less than. So you can see that this value is going to be somewhere here. And our decision boundary is somewhere here. It's 3, it's linear, it's 3, 3, right? So this kind of tells you that anything, when you add both of them together, if it's less than 3, it's in this class. If it's above 3, it's in the other class. This is just like a visual way of representing the decision boundary, what it is visually. So does it make any sense, please? Yeah. Next slide. So, this is what it is. Next slide. So cost function, what is cost function? What is cost function? Yeah, what's cost function? So what's cost function? Don't tell me so. I don't want to hear this so. It's obvious. Like it's some of error. Like what does it mean to like? What does cost? What do you use cost function for? So it tells you how good what. Thank you. So the cost function tells you how good your model is. That's what I want to hear. I don't want to hear some of error. I don't want to be hearing those kind of stuff. So let's just take this guy out. Or should I just let me We'll discuss this next week because there's a part that I kind of skipped. How many minutes do I have? 15 minutes, will be fine. This is the cost function you are familiar with, right? And I said that. Okay, let me ask you a question. What cost function should we use? Can we still use this? Can we still use this? Why? If you are going to tell me no, you have to give me a reason why you are not going to use it. Why? Just say it, like, it makes sense, it doesn't make sense, we'll find out. This is bondless, meaning? Okay.
That was the reason why we had to like do something to
Okay.
If you're using
Okay, he says, okay, there's something wrong with our age, something has happened to our age, right?
yeah.
Or if you have another opinion, like, let me get it. That's our own opinion. So,
like the other one, like our Y values have different values. But this one, like I said, it's bounded. We can only have 0 or 1.
0 or 1. So we have like distinct values for our Y. It makes sense. Any other suggestion? So I believe I like his answer. I actually like our own answer better because I don't want. It's not about. She was quite specific, but yours was more or less like yours actually gave us like an overview of what it is. We are dealing with a classification problem. We don't have like continuous value output like what we have for linear regression. Now we have like distinct value, but ours was quite specific because now our theta, our H value, our hypothesis has another representation. It's not like what we used to know before. It's not like this separately. It has something else now. It has logistic function. It has a new. It has been transformed to another form with the logistic function. So it kind of makes sense not to use what you have been using before. And another thing is just that this is just like what you said. This is for continuous value output. We need to have another way of formulating for distinct output. So next week we are going to talk about that. So to answer this question, what cost function should we use? We can't use this cost function anymore because of what? The first one is what? It's no more continuous value output. So what's the second one? Which is it's more or less like the same. So what's the second one? Our age has changed. Yeah. So next slide. So next week we'll discuss this. Next week we'll discuss next slide. Next slide. So let me talk about regularization. So this is how you overcome or you combat the problem of overfitting. So before I go into that, can someone explain overfitting? I gave one very basic example the last time. So I believe if the person can kindly return that example back to me, I won't mind. So it has to do with memorization during the exam. So can someone use that to explain about it? Or if you have a better explanation, fine. Let me hear. Yeah.
When the model is too good to be.
It's too good to be what? It's just like, do you understand that? Another thing. With what? Bazooka. How?
Waste of resources.
It's waste of resources.
Yeah.
It's basically like, I want to have resources. I just want to kill malaria. I want to kill mosquito with bazooka. See your resources. Why you mean? Okay, fine.
Memorize your textbook, your material, and thinking when you get to the exam, na grammar. When you get there, find another thing. And the original
that's so it's more it's like you didn't learn well. You are not generalizing well. You're supposed to see a problem, you solve the problem. But now you see a problem, you are stuck. You are just like, oh, based on what I've done before, this is the exact answer. But the problem, they have changed the problem. Oh, it's kind of close. What you are supposed to do is just go back and change the values. Like, okay, I know how to solve this problem. I have an idea. I've studied this problem very well. But you overfit is more or less like, I know the final answer. This is how the final answer is supposed to look like. No matter what the value is, this is where I'm going to arrive at. In as much as the lecturer have changed the value. So that's how I see overfitting. But in ML, it's like this, just like what she said, a situation whereby your cost function is 0 or is close to 0. You think you are doing well, but actually you're not really doing well. You must have overfitted. That's just like an overview of what it is. So a situation whereby you think your model is good, but what your model must have done, your model must have fitted well for the train set. Then when you try it with something else, in real life, it's not fitting well, it's not adjusting well. So at that particular moment, your model has overfitted for the train set, but not generalizing well in the scale of the problem. It's not even generalizing well.
Can we have a model that will be like 100% accuracy?
Yeah, and nothing is having 100% accuracy for your data set. Then in real life, where you're supposed to have 100% accuracy is misclassifying. That's another, like where you're supposed to identify this thing as cancerous cancer, is identifying it as benign cancer. Probably your model did not learn what it takes, did not learn the characteristics of what it takes to classify something between benign and cancerous. Probably it was learning color, or it was learning something else instead of learning the intricate features that are necessary for classifying both of them. Yeah.
So, just about prediction.
You need to predict because human problems are quite.
Is that only what it is about?
It's not just about prediction, but the bulk of it is prediction, so you can make better decisions. That's the point of prediction. Any other question? So I think that is how many is 10. So with respect to this, another thing overfitting can actually mean is when you have too much features. You have too much features. Let's assume you have too much features. You have too much information. You're not learning the most important thing. Just like what I said the other time. Like you are considering. You have okay. I want to predict housing price. I'm considering roof, tile. I'm considering gateman. I'm considering funny features. And in real life, you don't need those features. But what people think is that most times, they think that because you have machine learning, good machine learning algorithm. Once you apply good machine algorithm to bring your data, no matter the volume or the scale of your data, once you apply complicated machine learning algorithm to it, you have a good general. But actually, it's still wrong. You need to know what features are important. You know that the salary of the gateman is not important for predicting house price. You don't need that. The cost of the tile in the house, I don't know, you might need that, but to be honest, we don't really care about that. But we know location is very important, security is very important, social amenities, being close to social amenities is very important. These are features that are very important that your model should take note of, instead of other funny features like salary of the gatesman or cost of the tile. So therefore, as a machine learning person, what you are supposed to do is that, okay, you understand this problem. That's why understanding the problem is very important. We don't need this, we drop this, then we accommodate for the ones that we need. Or another thing you can also do is that even in as much as we have all these features, well, we are not going to take these features too serious. These ones that we don't necessarily have to take them too serious. We'll leave them there, but we are going to penalize them. We won't take them too serious. So next week we'll discuss how we do that. So basically, regularization is a way of penalizing those features, those redundant features. So that's the end of the class. See you next week.